Merhaba arkadaşlar. So we will be continuing the discussion with chapter 12, which is basically the last part of the course, and it's going to involve basically the abstract data types and the dynamic representations in Java and also in general programming languages as well. So this is going to basically related to collections, which is a dynamic structure to keep track of the data in a uniform and nice way. So basically we will use collections to organize and manage different objects. And if you look into the topics that is covered in chapter 12, you can see that what's the concept of a collection, the separation from an implementation versus the underlying implementation versus the usage of that by the users, and then dynamic data structures. This is the main part of the course, this chapter, dynamic data structures, which is basically the linked list, doubly linked list, and other structures that we will see. And if you look into the structures, as I said, linked list, queues and stacks, trees and graphs, and generics, we're not going to really touch much onto that, but it's a nice feature of Java as well, the generics. It's also available in other object-oriented languages. So what basically provided by generics is that it provides a generic methods and implementation details which you could use to apply any kind of object, such as, for example, if you'd like to apply it for a string, you can apply it. If you'd like to apply it for a student class, you can apply it to a student class, or any kind of objects that you can use in generics. But again, we're not going to cover that in this course. So if you're interested in, you can you can read, and we can discuss more if you like to. So when you look into the collection, so the collections are provided to serve as a repository for collecting the objects. So you can have multiple instances of the same type of data in a certain in a certain fashion that you can access, delete, add, remove, different things that you can do with them. You have seen some sort of something close to this. Array list is a kind of a collection which provides uniform access features for your data or objects that you would like to implement. So as you see, you have you're provided with some add, remove, and managing, sorting, and different procedures that are available for the collection you are targeting. And these could be ordered or unordered, that doesn't matter, but the idea is to write the collection such that you can keep track of the data in the same way it is originally defined. For example, if it is always sorted, you need to insert the data, then you're going to insert this data into the collection such that it is still sorted after this insertion. So basically, it continues to have the same features available to you at the beginning of the creation of the collection. These collections could be homogeneous or heterogeneous, so it's up to the designer to design how to handle these collections. And the collections basically provide an abstraction methodology. What we mean by abstraction is that you do not reveal the details. The user does not deal with the details of the implementation, but rather what user cares is how it is used and what he or she can do with this collection. So abstraction at the end gives you that opportunity so that you don't deal with the details. You say, hey, I'd like to add this, you add it. I'd like to remove this, you remove it. But in the internal implementation, you don't really deal with how it is done and what are the things that are used, whether it is dynamic or static. You don't care about that, but what you care is only the usage. So abstraction provides that. So the unneeded details are hidden from you in the abstracted data types. As we will see with different abstraction levels, you can hide some or more or most of the details that are not relevant to the user at all. So this is going to help you to manage complexity and make it possible to change the implementation without changing the interface. So you basically have an upper level that user is dealing with. This is the upper level where user is basically sending requests such as add, remove, whatever that is needed in terms of operations. However, in the underlying implementation, you have an abstraction here, which abstracts this from the user by these commands, and the internal implementation is up to you. You could use an array to implement a certain thing, whereas you could use a linked list instead of that too. So the user doesn't really care about this. Or for example, sort. You have a sort algorithm. You don't care about which sorting is being used, but you only know that, hey, whenever I would like to sort them, it sorts me out. Whatever the data that you have, it will be sorted out. So basically, abstraction provides this hiding for the users, and it's more, you can just modify and rewrite this whole thing from scratch, and the user still will be able to use the same thing as before. So it basically allows you to perform modifications easier and nicer. Abstract data types is a way to manage this. In general, this is all used in any language that you find out there, basically in the object-oriented methodology. So abstract data type provides you an organized collection where you can, manipulate the data with certain commands. But, the operations that you have in the abstract data type, ADT, this is the common keyword that's used, the shorthand for abstract data types. The operations that are defined for this ADT is going to basically indicate what are the capabilities provided to you in your object collection. As I said earlier, how ADT is implemented is not a concern for the user, but rather how he or she can access these features is what matters to that, and that's abstraction again. So you have ADT implementation here. However, ADT methods are on this part of the hierarchy. So the dynamic representations is one of the structures that is used by any kind of language. So if you think about the static data structure, what we mean by static is that it has a fixed size in terms of the representation capabilities. Can you give an example of a static data structure in Java? So it will have a fixed number of elements that it can store. An array, right? In an array, what you do is basically, whenever you create the array, you specify how many instances of integers, let's say, it's going to take. So you say that, hey, I'd like to create an array that is going to take 100 integers in it. So you basically have a static representation here because you only have a fixed size of 100 elements. However, this may limit your capabilities, as we did with the enlarging the CD collection, if you remember. You remember the CD collection example? So in the CD collection example, we were initially starting with 100 CDs, let's say. However, as we add more and more CDs, if the area is not sufficient, if we need more space for the CDs, if we have, let's say, 150 CDs, what we were doing was we were just multiplying with this 2 and then getting a new size for 200 CDs. So basically, this manipulation is needed to create a new data structure from scratch and copy everything onto that, which shows the problems with the static data storage. So this is basically the problem with the static data structure. So you have to, every once in a while you may need to make it larger or get it smaller and so on. So you have to do this manually. However, if you, instead of use a dynamic structure, dynamic data structure, it will dynamically shrink and grow with every adding or removal of your objects. So as you add, you will increase the size. As you remove something, you will decrease the size. This is called dynamic data structure. Okay, so this is today's lectures are mainly concerned with dynamic data structures and mostly with the linked lists. So in a dynamic data structure, you use links to represent this dynamic nature. So let's say I have an object that I start with, and then every time I add another object, I have a link to add to after this. And then if I add one more object, I have another link that points to the next object and so on. So you dynamically, whenever you add at the end of the list, and then you continue. We will see the linked list features shortly, and it will be more clear what I mean by the dynamic data structure. So if you remember, in Java what we use is the object references. So for example, if you have a student object which is composed of the name, the ID, and then the GPA for the student, for example, you have a reference for the student. So you create the student object, right? And then you have the reference to that object. And you can use this feature to enable this dynamic data structure. So how are you going to enable that? If you recall this kind of student, how can I create a class for student class? Let's write this class. Public class, and then let's say I have the student class, right? And so the parameters that you're going to have here are string, and then let's say I have the name, and then string ID, right? And let's say I have another instance variable for my class object. Let's say this is the GPA, so I will have just a double to indicate the GPA. Okay. So this is kind of, you obviously have methods and other rest of the things. I'm not going to write those. But what you have here is the object, that you can create with this kind of thing. And whenever you create new student, right? Let's say you have the corresponding constructor with these arguments. Whenever you create, let's say I have P equals new student. Obviously, it's type of student. And this way, you will get this P to refer, right, to this student object, and then this is an object reference basically. This P shows indicates an object that is type of student. And if I'd like to do a dynamic representation here, how can I add a link to my class definition? So if you would like to add, let's say, a reference to another student object, how can you do that? So I'd like to basically have here, this points to an object, and then within this object, I'd like to point another student object of the same type. So if I write here another object such as student next, is it going to be possible? So here I have the string, and then the double values, and then I also have a reference which basically is a reference to another student object. So I have another student which is identified by next. So my next field is basically a pointer or a reference that is pointing to another student object. Okay. So in your constructor, what you could do, for example, in the constructor, how do you do this? Let's say I'd like to have a constructor for my student class. How do I define it? Basically, you will have the string, right? And then you have another string for the ID. I'm not going to write the details. And ID, and then let's say double GPA. And let's say that's it. Okay. So I can have this constructor by writing these details. It's going to be this dot, name equals name, and then you will have this dot ID equals ID, and then this dot GPA equals GPA. Basically, for the initial starting point, I could say for the dynamic representation, the next of this this object is going to be, you could say this dot next. To start with, I can say, let's say I don't have anything there that's assigned to this next field. I'll assign it to be null. Okay. So you can initially start with an object, with a student object that doesn't refer to anything here. So it basically refers to null pointer. And then whenever I'd like to set next, you can set the next field of this student object with another student object. So you create this dynamic structure. Okay. Basically, the main idea is that in the definition of the class student, you also use as an instance variable of itself. So you see that it's kind of a reminding recursion, but basically you have a pointer or an object reference that is of the same type of your class. So that's how you would get the dynamic behavior in representation. So it will be more clear with the linked list as I will show you shortly. So as you see here, you have the student class that contains a reference to another student object. Basically, you have the same student. However, you have this additional next reference, which is of type student, and it points to another student, which is Jane Jones. And then it also has another next field, which is at the moment is set to null here in this example. Okay? So basically, having this pointer will enable you to dynamically grow and shrink as you add more and more elements into your structure. Any question? So if you continue adding more and more students to your list, you can basically create linked structures, something like this. So you have one student that is pointing as the next student as this one, and then this points to next student with this one, and so on. So you could, do very nice things with this. For example, if you'd like to do a sorted list, how can you do that? Let's say I have a field that is keeping my list as integer values, let's say 1, and then I have a reference which is basically composed of two fields. One is the instance variable, which is the integer, and then the second one is the object reference, which is this field that is referring to. So in this case, let's say I have a sorted list, and then you have, let's say, 3 here, or 5. And then you have the null pointer at the end. And if I'd like to insert initially into this list, let's say I'd like to insert 4. How am I going to insert this? So you can keep track of this in a sorted fashion. In arrays, if you remember, if you had the array, how were you going to do this? So it was going to be 1, 2, and 5, right? You would have copied this to here and then insert 4 here, right? So that's basically the thing that you need to do in an array. If you have lots of elements here, right, this is going to be really complicated to perform. So you have to switch all the elements to the next element and so on. So you have to perform a lot of operations. However, in the dynamic representation, if I need to insert this 4 into this list, what do I need to do is that I'll just take this over here. This is going to be 4. So I'll first set this next field to be pointing to here, right? And then I will remove this from here such that it points to this one. So I will be able to insert it in the right position that I'd like to insert. Okay, basically this shows the capabilities or features that is provided with the dynamic structure. So in a dynamic structure, you can easily insert something without ruining the rest of the representation. However, in the static case, you have to swap a lot of things depending on the case that you are working on. So in a linked list, basically, it consists of a sequence of nodes, as I said earlier, and each node contains a value, such as this one. It could be anything, any object. It could be primitive types or any type that you have declared yourself, doesn't matter, but you have a value that is contained in the node, and then there's a link to the next node that is indicating, or a reference to the next node in the list. And the last node, which is D in this case, is going to basically have a null pointer which doesn't point to any object in the list. So you can also have a header that to start with points to the first starting point of the list, or you may not have it, but usually in the implementation you have a header that indicates the starting point of your list. Okay? So there's terminology which is obvious. You have the successor, which indicates the next node of the current node. So the successor of 2 is 4 in this case. Successor of 4 is 5. And then similarly the predecessor. Predecessor of 5 is 4. Predecessor of 4 is 2, and so on. So you just have the successor and predecessor indicating the sequence. And then also you obviously have the length, which could be kept in this list header. So let's say this is your my list. How could you define this list if you need to student list? Let's say this is type of student list. How am I going to define the header for the student? So I'd like to define this here. Public class student list. I'd like to create this to indicate the header. So what does header hold in it? It could hold the first, right? So you will have a first field which is going to be of type. What type is that? It points to a student. So it has a student which indicates the first or head or whatever you call it. You know, you have this. And then also you can have the number of students that are kept in this student list, which could be, let's say, an integer count. So whenever you start with, you'll start with first is equal to null. So initially this will point to null. And then as you add one element, it is going to point to that one and so on. The count will be incremented by one every time with an additional object inserted into the list, right? So you basically can keep track of a student list, which is of this myList type. And initially it points to one student object, right? That's it. That's what it points to. And then each student object is also have a pointer, pointing to another student object internally. So you can keep track of this list length using the internal representation of the student list, which is going to be kept in the count. As you remove, you will decrease the count by 1. As you add, you will increase by 1, and so on. In C++, there are pointers. In C and C++, there are pointers that are used to represent these linked list structures and dynamic structures. These are similar to what we see in references, object references in Java. So you could use both for, for referring to the dynamic data structure. I will, use pointers and references interchangeably, so they mean the same thing, basically. So as you know, you create a reference in Java using the new person. So in this case, for example, if you would like to define person P, new person John, so basically P is a pointer or an object reference. That is the object defined by the John name, and the corresponding features of the John could be modified as well. So how to create this list, basically, if you look into this, let's say you have in the list definition, you have the myList, which points to an integer, and the object that is referred to by 44. So in this case, you have in the myList, let's say this is going to be so if I'd like to define this, how am I going to define? If you look into this, so I'd like to, let's say, public class node list. Okay, and then I will have, let's say these are nodes of type node. I'm going to basically say public class node list, and then I will have a node object that I'm pointing to, node, let's say, head. And then int count, which keeps track of the number of elements in my list. Okay, and then for the node object, how am I going to write the node object? Public class node. Basically, it's going to have the int value, so which keeps track of the integer value, and then I will have a next field. What type of object it's going to be? It's going to be a node object that is pointed by the next pointer. So you can again have the constructors and necessary things here. For initial constructor, you will have count equals 0, and then head points to null, for example. And then for this one, you will have int value that is, that could be a constructor that takes an integer. So your constructor will take only that integer and then initialize it to that, and then your node next is going to be basically a null node. As you add, you can modify things in the node list to add the additional nodes. So here, in this case, if you have the constructor, something like this, so class cell, so every object is defined as cell, int value, so you have a value, and then cell next, which indicates the next cell that you're referring to. and this is basically the constructor which has a value and the next cell. So you can have this kind of constructor which assigns the value to V, and then next element to be the referenced cell which is given here as N. And basically this is the constructor. So if you were given this constructor, how could you define this list? So basically you can start with defining the rightmost element, cell temp, so it's a type of cell object, and then you create this with the constructor new cell 17 and then null. As you see, the first argument is the integer value, which is this one, and then the second argument is the cell object which it points to is initially set to null, so you basically point to null. And then after that, if you would like to create the 23, how are you going to create that? So you're basically going to do the same thing, new cell and then 23 comma temp. So you'll basically use this temp as your reference that is pointed to. So as you see, they call this new object as temp again, so the original temp is gone now. However, you just have the new temp which is going to be 23, and then its next is this temp. However, you're done with that temp, no longer it points to 17. From this point on, it basically, at this point, it will basically point to here. So this is what temp points to at this point. And then whenever you want to do the same thing over with 97, what you're going to do is that temp equals new cell 97 comma temp. Now I'd like to assign this new object such that its next field is equal to temp, which is this one, right? And then I'd like to initialize the integer value to 97, and after that I'd like to call it as temp again. So my new temp value is basically going to be this one. So it doesn't have to be the same variable that you use. You could use some other variable, but it's not necessary to repeat the same thing over and over. So you can just get rid of those additional variables that are defined here. So you could basically do this as temp2 equals this, and then temp3 equals temp2. Perfectly same. And then the last thing, cell mylist. So it points to a list object, cell object again, and then my list is going to be of type cell, and it is going to basically point to this object which has the 44 integer, and then as next it has the temp, which is going to be something like this. Okay, any question? So this is not really complicated, but what makes this complicated is adding new elements or deleting elements and things like those. The operations are a little bit harder to manage. And if you look into the singly linked list, in what we mean by singly linked list is that there's only one single reference from one node. As we will see, there's also doubly linked list, which is basically, although you have pointers towards this, you also have pointers to backwards to the object. This is called doubly linked list. That's why it's called singly linked list or SLL. So in each node you have a value and a link to its successor. So you have B as A's successor, C as B's successor, and so on. And also you have the header which points to the first object, the first node in the linked list that you have in the implementation. So if you would like to define the single linked list SLL, you have the private SSL node first, as I mentioned to you earlier. So you define the first node, which is basically going to assign initially with the constructor as null, and then you will have add and remove methods to the SLL. So the class describes the header of the single linked list, but you can access the whole list by using the first node, and you can trace all the links and reach to the element that you're looking for. For example, if I say, in this case, if I say my list dot next, you can put parentheses if you like. So what am I going to reach here? you'll basically get my list next is this one, right? Or no? My list basically is this one, right? So my list.next means this, and then if you get the other next, it's going to be this one. Okay? So you can reach anything using the next and the reference that is pointing to the next element. So if you look into the SLL node, so one is the SLL, which is the whole list, and then this is composed of SLL nodes, right? So each element in this list is going to be SLL node, right? And if you look into the code here, public class SLL node, it has the object that is referred to by the, the element. It could be an integer, it could be a string, it could be any type of thing that you would like to refer. And then you have the successor or next defined by variable in the implementation. And this shows the constructor. Basically, you have a constructor which takes the object and the successor. So you can, set the corresponding instance variables to those values. So let's say if you would like to create such a list in your implementation, you can use this SLL numerals new SLL. This way you create the numerals, and then to do that you can use numerals.first is equal to new SLL node 1, new SLL node 2, new SLL node 3, and then null. Basically, if you go backwards here, you see that you create a node that is given with these features. So it has the string 3 and then a next value that is equal to null. So you basically create the numerals and then you create the 3 with this new object creation. And then you next create this. However, it is value is equal to 3, and then the argument, the next object is basically this object. So it points to the 3 object as you do this. So now you have this part covered, and 1 is going to be the string that you would like to keep as a value, and then its next will be this node, the 2 node, which is created just with this statement. So it's basically going to point to that, and then once you look into the first element of the numerals starting point is going to be this one, which is created by the first new statement, as you see here. Okay. So basically, you could do this. You could separate this into 3 additional statements, right? It will be the same thing. How I could separate that? So I can say, instead of doing that, I can say SLL node 3 equals new, and then SLL node 3 and then null. So I created the rightmost object, and then I create the second one, SLL node 2 equals new SLL node 2, and then I have what? Node 3. So this is essentially the same thing as you do there. But instead of defining individual variables, you just do it at the moment right in there in the spot. So you can do the same thing for SLL node 1, which is equal to new SLL node, and then you have 1 and node 2. Right? So basically, it's the same exact thing as you do there. Any question? So how to traverse an SLL, single linked list? How can we traverse the elements of a linked list? How can we traverse? Let's say I'd like to write a for loop to traverse, and public void print first to last. So I'm going to basically write all the elements when I call this method. For example, this is SLL, and I create, if you go back here, this is numerals, right? SLL numerals. So I'd like to call this method numerals dot, and then I'd like to print all the elements. Print first to last. And I'd like to write the internal implementation of this. How am I going to write this? So what is the starting point here? You basically start with the header, which is the starting point, and then you will say for, right? How am I going to write the for? Or while, you can use while. While the next element of the last thing is not equal to null, continue, right? And then in the implementation, in the internal implementation, you'll just get the object's string value and print it. So if you look into the implementation, for SLL node current equals first. So I start with the initial first header, which is the starting point for my loop, as my current is equal to first. Current is not equal to null, so this is the continuing condition. If current is not equal to null, I will continue, right? And then every time after I'm done with the current instance, current iteration, I will get the current successor, which is the next element. Okay? So basically what you do, you'll then system out print current dot element, and then you put a space. So you will start with the first element, which is initially first. So let's modify this. So you'll start with the first, and then your current basically points to the same object, because I assigned current that's equal to the first. And then I will go, is current equal to null? No, it's not equal to null. And then I will print out the current element on the screen. And then after that, I will update my current to be current successor, which is current dot successor is pointing to this. So my current is going to be pointing to this value now. Okay, and then I will check, is current equal to null? No, so I will print that. And then I will update my current to be again current dot successor, so that it is going to point to this new element. And then so on and so forth. So you will be able to traverse the whole list from starting with the first element of the linked list.
Elementle current successor yazdınız ya. Onlar Java'da tanımlı şeyler mi? Yani o elementle successor dediğimiz ne oldu?
Let me go back. So as you see, object element is defined to be the element that is kept in the first part of the reference, and then successor is defined to be the successor of it. So it's instance variables. Okay? So it's like the instance variables that we used for value and then the next. So let's say I have public class node. I have a node object, and then in that I have int value, which is the instance variable, and then I have the node that is referred to here as successor or next, doesn't matter. So these are basically indicating that. So it's essentially the same thing. If you look into here, if you look into this traversal, you see that you start with the first element, and then you every time get the successor by assigning the the successor element or node. Does it make sense? So this could be an instance method for the singular linked list to access all the elements. So again, you start with the first element, and every time you check whether the current is equal to null or not, and every time you continue with the next element, which is going to be obtained by current. So my current points to this one, let's say. My current's next is basically pointing to this, so I will update my current to be now pointing to current.next, or the successor, doesn't matter. So if you see the animation, that might make it more clear. So I have a current variable that is going to be initially null. However, I will assign current is equal to numerals dot first. So I will assign it to be numerals dot first so that it points to the same object as my numerals object's first reference. And then I will update my successors to be my new current so that I will point to the 2 element, and then it will update with the, if you remember this statement, current is equal to current dot successor. So it basically points to the next node in the sequence, and it will update my current to be the successor of the current node. So this dashed indicates this assignment. And then once I do that, I will update my current to be the successor of 2, which is going to point to 3. Any question? So in the end, it is going to assign the 3's successor, which is basically null. So it will finish the loop at the moment where you reach the null pointer at the end. So to insert a node into the SLL, how are we going to insert? So there are different options available to insert a node. You could insert it as the new first element. So how am I going to, let's say I have let's say this is first, and then I have 1 here, 2 here, and then 3 here, and this is basically a null pointer which doesn't point to anything. If I have here, if I'd like to insert as the new first element, what do I need to modify here? And I'd like to insert, let's say, 0 as the first element. And it's initially obviously null as the next pointer. So how am I going to insert this as the first element? So what are the things that I need to do to insert as the first element? So now when I'm done, it is going to be here at the beginning, and then my first is going to point to that. Come on. So basically, you need to point to this element after this, right? So you need to make sure that once it is inserted, it's going to point to 1. So you will say this node's successor, let's say this is A dot successor is equal to first, such that it is going to point to this one. So it's A dot successor is equal to first now. So it's pointing to the correct thing. What do I need to do next? I will update my first. Instead of pointing here, it is going to point to this one. Right? So my first is going to be equal to A. Right? So it's basically the insertion procedure at the beginning. So if you would like to insert as the new first element, you can do that. What if I'd like to insert this as a last element? Let's say I'd like to insert 4 as the last element. So this is equal to null initially, and I'd like to do that. How am I going to insert as the last element? So you have to first find, you have to have a pointer that points to the last element in order to do that, right? So you have to first reach here such that you can add the element as the last element. So you will basically have a traversal which is going to check with the successor every time until this successor is equal to null. It will continue. Once the successor is null, you will say that, hey, let's say this is temp. Temp's next or successor is null. While temp, right, dot successor not equal to null, I will continue. I will get temp equals temp dot successor. So every time I'm going to get the successor of the current element, so it will initially start with temp equals. Initially I will start with the, let's say this is first. Temp equals first. So I started with the first element. I check temp is pointing to the same element as this one now. I check temp's successor, is it equal to null or not? No, it's not equal to null, so my temp becomes temp.successor, so I'm now pointing my temp here. And then the next thing, I will check temp.successor is not equal to null, so I will assign my temp successor. And then I will check again with the successor, is it equal to null? No, so I will update my temp to be successor. So when I come to here, temp.successor is not equal to null. Is this the case? No, so I will exit the loop. So I found the last element. Then what do? I will insert it as the last element. This, let's say A. What do? The only thing that you have to do is basically temp dot successor is equal to A. Right? So you basically, instead of this null pointer, temp.successor, which is this pointer, point to 4. Okay? So similarly, any question? Similarly, if you are given a node specified by a reference, let's say you're asked to insert this before a reference given as B. So this is, let's say, B, and you're asked to insert an element that is equal to, let me remove this. So this is first again, and you're asked to insert this element 1.5 and null. Let's say this is A, referred to by A, and then I'd like to insert this before B, which is this one. So how am I going to insert this before B? Exactly, so you have to first find that the elements next is equal to B. So you have to find the position where you have to insert. So you have to insert here. In that case, what you're going to search for, while, right, temp dot successor not equal to B. So I'll continue to search for the next element as B. So when I found 1, oh, okay, I see that the next element of 1 is 2, so I will need to insert it here. So I will continue until that. Until that time, I will say temp is equal to temp.successor, so that every time it's going to get the next element, on and on. When I find it, whenever it's the next element, what am I going to do? So that means temp is pointing to this, temp.successor is equal to B. So they're pointing to the same thing. In that case, I found that temp's successor is B. So what am I going to do? I will say that temp.successor is equal to, so I'd like to make that this temp.successor as A, and then A.successor, which is going to assign this to this, so I'll need to say B. Okay, so this is going to be the, obviously you will have additional code here, but I'm just giving a sketch. So you need to assign temp initially to first, and also check for nulls. You know, you may not be able to find it in the list at all, right? If you cannot find, what are you going to do? So you have to also check for that. Okay, let's give a break and then we'll continue.